Each of the three terms of the binomials that we see here are considered to be perfect squares. And these binomials are sometimes called also the difference of two squares. And they can be generated by multiplying the sum and the difference of two monomials. So what that means is we can look at this, just looking at this, we can say x minus y times x plus y. That's the answer. All right, we unsquare each one and we say x. We say the first one minus the second one, the first one plus the second one into two separate entities. Same thing here. We would put a radical sign over this or just mentally unsquare it, right? So this would be 2p minus 25. The square root of 25 is 5. And then we repeat it over here and just say plus 5. Same thing here. We have m minus 4 and m plus 4. And that is how you would factor the difference of these squares. And these are all exactly correct without actually having to do a whole lot of mental math. It's a format and a formula that we can use successfully each time. And I'm going to prove it to you. So for this first one, we're going to do what's called stacking. I'm going to say x minus y, x plus y. And I'm going to show you this method of multiplication. And it's a distribution method. We're going to say y times this gives me a minus y. Y times this gives me a positive xy. X times negative y gives me a negative xy. And actually this is y squared, sorry. And x times x gives me x squared, and it's a positive. So when I combine these, positive and negative, identical, cancel, and I'm left with x squared minus y squared. Same thing here. If I say 2p minus 5, 2p plus 5, and I multiply. Positive 5 times a negative 5 gives me a negative 25. Positive 5 times a positive 2p gives me a positive 10p. Positive 2p times a negative 5 gives me a negative 10p. And 2p times 2p gives me 4p squared. The middle terms cancel, and I'm left with 4p squared minus 25. Same thing here. It is a repeating pattern that we can count on each and every time. M minus 4 over m plus 4, right? This gives us a negative 16. This gives us a 4m positive. This gives us negative 4m, and this gives us m squared. These cancel. M squared minus 16. The very act of making one negative and one positive and having exactly the same terms guarantees the fact that you're going to have two middle terms that are identical except for their sign, which is going to make them cancel each other out. So you're only left with the beginning and the ending term. Now this only works if you have a minus sign, and both of these numbers are perfect squares. If this is a plus sign, it does not work. So that is something you have to watch for. Make sure that it is a minus sign, okay? So let's do a couple of practice problems. I'm going to let you do these yourself because these are so straightforward. All right, we have 73.1. I want you to factor, actually I'm going to put up a few. Hang on just a moment. All right, so I have three perfect square binomials, and I would like for you to pause the video, factor each one of them, then press play, and see if you got your factors correct. So I want you to go ahead and pause and work these out. Factor them for me. All right, so first I have to apologize. I wrote negative 36x to the third power. It should have been to the sixth power. Apparently when I wrote it, I was already factoring in my head. that should have been a 6. So if you had trouble with 73.4, it's my fault. And if that clears that up for you, okay, that should tell you what I did wrong. All right, so the first one was 73.1, negative 4 plus x squared. Well, we know that it has to be a minus. That second term has to be a minus. So all we had to do here was rearrange x squared minus 4, and then we could factor x minus 2 times x plus 2. 73.2, it was already in the right arrangement, so we just had to get the square root here. That was 7m. So this was a, 7m minus a, 7m plus a. And it doesn't matter whether you do plus or minus, first or second. It's the same either way. This one was a negative first, then your positive, so we rearranged it so your negative was in the right place. And then we took the square root here, 5y, plus the square root here, 6a, times 5y minus 6a. Same thing here. This should have been, like I said, x to the 6th. So if you had a problem with that and had a question about it, that's what it was. So if you don't get this one right, don't feel bad. I didn't give you the correct information on the front end. So we just had to rearrange this just like the others, and it ended up being 7a minus 6x cubed y squared times 7a plus 6x cubed y squared. So you could see there is a pattern and a relationship here that we have to follow. It has to have the minus sign, and these have to be perfect squares. If you could take this number right here and put it under a square root and get a result that's easy to see, that's easy to factor, then you can do it. And if you could do this to both of these, then you'll be just fine. Then you can factor everything within it. All right, moving on. We're not going to spend a whole lot of time on that because it is a very, very easy concept to master. Let's clear the page and let's talk about probability without replacement. So far, we have talked about successive random selections of marbles from an urn. But we've always put the marbles back in the bowl. We've never left them out. So now we're going to talk about what it looks like when we take them out and leave them out. So if I have an urn, right, or a bowl, let's just say I have a box because it's the easiest thing I know to draw. And within that box, I have, let's say I have 3 blue marbles, right? And then I have 4 red marbles. Actually, this says I have 7 blue marbles. So let me put more blue marbles in here. 1, 2, 3. My blue marbles don't look that great, do they? So I have 1, 2, 3, 4, 5, 6. I need one more. That's going to be 7 marbles. And they're agate, so they're not solid color. All right, so I have 4 red and 7 blue marbles. So our problem says that 2 marbles are drawn at random. What is the probability that the first is red? Okay, so the probability that the first is red and the second is blue if the marbles are drawn with replacement, okay, and then without replacement. So let's see, A is with replacement, B is without replacement. So let me show you what that looks like. So the probability that we draw a red and then a blue. So for us to get a red, there's 4 reds, right? There's 4 red and there's 7 blue, which gives us a total of 11 marbles, right? So the probability that we're going to draw a red is going to be 4 out of 11. Okay, so this is A with replacement. So if I put that marble back, I put this red one back in, and now I want to draw a blue one. There's 7 out of 11 that could be blue. So I say 7 out of 11. So times 7 out of 11. So that's going to be 28 out of 121. That's going to be my ratio, and then I can reduce that to 14 out of, is it 55? No, I can't reduce that. 121 is not reducible. All right, so that's my ratio. 28 out of 121 is my chances of getting red and then blue when I reach in my hand. And that's if I put them back in there. So what about without replacement? How does that work? Okay, so it's just what it says. It means that you're not going to put that marble back in here. So let's do B here, without replacement. So the probability that I'll get a red and then a blue, but without replacement. All right, so that's going to be, when I put my hand in, I've got 4 red ones out of 11 total. So I have a 4 out of 11 chance, right? But I keep that red one out. So I erase a red one. Now this changes. So now I have 3 red, 7 blue, but only 10 marbles total. So now when I take my second draw, because the number of marbles has changed, my probability is going to change. So now I have a 7 marble. So I have a 7 marble opportunity there, but only out of 10 marbles because I kept the first one out. So you see how that total number reduces? So now I have a 28 over a 110 chance, which then reduces to 14 over 55. So you could see how your chances to get what you want increases whenever you take possible options away. So let's do one more using the same scenario. Only this time we're going to go for a longer probability. And let's do A with replacement, and B is without replacement. All right, so I want the probability that I am going to get a red, blue, blue, red, red. That's what I want to draw. So here's my probability. Here's A with replacement. So let me put my red marble back in the bowl. Okay. Let me move this down a little bit so I have a place to do a little bit of math. So with replacement means my probability for a red, blue, blue, red, red. Okay, so I have 4 red and 7 blue, 11 total marbles. So my first chance is going to be 4 out of 11. Let me move this up. I'll move this over. I'm going to put it right here. That'll work. My first chance, the red. So there's 4 red and 11 total marbles. Okay, put that marble back in. This stays the same. So for a blue, I have a 7 out of 11 chance for a blue, right? So this is red. This is blue. Now I want another blue. So another blue. The marbles keep getting put back in, so the chance to draw that stays the same. Now I want another red. 4 over 11. Because I'm putting the marbles back in, the opportunity to draw that remains the same. 4 out of 11 is my chance. So the probability that I would draw the marbles in 5 draws in this order is going to be, let me do the math here. We have 4 times 7 times 7 times 4 times 4. So 3136 over, I have 11 to the 5th. So it's 161,051. So 161,051. And if I wanted to, I could take the time to see if that will reduce. I'm not going to do it right now because I just want to see how this works without replacement as well. So let's do this without replacement, okay? Again, P, R, B, B, R, R. All right, we'll put those in the same location here. We start with 4 red, 7 blue, total of 11 marbles, right, for the first one. So the first probability is going to be 4 out of 11 because that's our starting point, all right? We take that red marble out and we keep it out. Now we have 3 red and 7 blue out of 10 marbles, right? So our next chance is blue, but it changes. It's 7 out of 10 now, and that's for our blue one. All right, and that blue one, we keep it out. We don't put it back in. So now let's do another blue one. Well, now we have 3 red and 6 blue for a total of 9 marbles, right? Let me move this over. So our probability is now 6 over 9 for that blue. You see how it's working so far? Now I want to pull a red. So we pulled one blue out, so we're going to pull that other blue out, and he's gone now. So now we have 3 red and 5 blue and 8 marbles. Now we want to pull a red. We've got a 3 out of 8 chance that we'll pull a red because we have reduced the number of marbles each time. So now we're going to get rid of that red, leave it out. So now we have 2 red and 5 blue for a total of 7 marbles. So now for this final draw of red, we have a 2 out of 7 chance to pull a red. Now we'll see what our probability is for this. So we have 4 times 7 times 6 times 3 times 2 is 1008 all over. And this is going to change because the quantity marbles changed each time. So 11 times 10 times 9 times 8 times 7 is 55,440. 55,440. Do we see how much that ratio has changed? So we know now this is divisible at least by 4, possibly. Let's see. 1008 divided by 4 is 252. Let's see what this is divided by 4. $55,440 divided by 4. Will it divide? Yes. 13,860. I think that'll divide even more. Let's try that. See if we can divide that in half. Let's try 252 by 4 again. Will it divide? Yes, that goes to 63 over, let's see if we can divide this by 4 again. 13,860 divided by 4, 3465. All right, so we've been able to reduce this one so far to 63 over, oops, wrong button. I needed that button. 63 over 3465 so far. So we can see kind of where our chances are. Let's see if we can reduce this one at all. I'll start with the denominator just to see what we can get. That's going to be 8 9 plus 5 is 14. Let's see if we can divide that by 7. 161,051 divided by 7. Nope. 161,051 divided by 3. Nope. 161,051 divided by, oh, I don't know, 11. It should be 1,400. All right, let's see if we can divide this. 3136 divided by 11. Nope. So basically, this is it. These are your chances. We can't divide this by anything. Not that I can tell. This 63 is going to be 9 times 7. Let's see if 3465 is divisible by 7. No. Yes. So 495. And this is 7 times 9. So this is 9. So yeah, that's probably as small as we can go. So our chances of getting this draw without replacement is 9 out of, and I did it again. That's not what I wanted to do. I wanted to do this right here. It's 9 out of 495. That's slim pickings. That's a small chance, right? And actually, I think this could be divided by 9 too. Let's try that. $55. So you have a 1 out of 55 chance of getting this draw without replacement. I don't know why I spent all that time on reducing, just because it was fun. But how cool is that? How cool is that we have a 1 out of 55 shot of getting that? So if you can reduce it, you still have a really bad chance over here of getting the draw that you want if you keep putting the marbles back in the box. But that's okay. That's all right. The main thing is that I wanted you to understand that whenever you don't put something back in, like let's say you've got a bowl full of M&Ms and you want to find the red M&M, but you keep putting the M&Ms back in the bowl if you're not getting the color you want, your chances are much better of getting the red M&M if you eat the M&Ms that you pick out. You'll eventually get to the red one. So, as silly as that sounds, so it does change your probability from one to the other because you have to account for the change in the environment of the box or the bowl or whatever's going on here. It does affect your outcome of what could happen. All in all, it's a pretty fun lesson, and you could actually get you a bag of M&Ms and test it out and see what you get versus what your probability tells you will get. So maybe have fun with this and try it out. That's all I have for now, and I will see you guys in lesson 74.